Jai Hind everyone. In the subject of electrical machines 2 KEE 503, I am going to cover the topic of speed control of three-phase induction motor. This lecture is actually in continuation with the previous lecture on the same topic, where I have covered certain topics of speed control of three-phase induction motor. So let us just go for a revision of the same. After that, I will cover the rest of the methods which were left in previous lecture. As we know that rotor speed of three-phase induction motor is given by this particular formula, which is Nr equals to 120 F upon P, where 120 F upon P is nothing but the synchronous speed Ns of the rotating magnetic field into 1 minus S, where S is the operating slip. So from here what we can see is the speed of rotor is dependent upon the supply frequency, number of poles for which the machine is wound, and the operating slip of the motor. So let us see what are the various methods of controlling the speed. So one way of classifying the methods of controlling the speed are, from the previous slide itself, we can see that it is dependent upon the frequency, upon number of poles, and upon the operating slip S. So the speed control methods can be classified in three categories: frequency control method, number of pole changing method, and the slip control. The other way of classifying them is actually based upon whether the speed control is exercised from the stator side or from the rotor side. So as per this classification, the methods can be classified as the methods which are exercised from the stator side. They are supply voltage control, supply frequency control, and by changing the number of poles. If you recall here in this formula, number of poles P are appearing, and the operating frequency, supply frequency F is appearing, number of poles P were appearing, supply frequency F was appearing. The third method which is mentioned over here is actually the slip control method. So supply voltage control actually varies the operating slip of the machine and hence the operating speed of the machine. From rotor side, the methods are adding external resistance in rotor circuit, cascade control, and injecting the slip frequency voltage into the rotor circuit. In previous lecture of the subject, in previous lecture of the topic, I have already covered the speed control methods which are exercised from the stator side. Supply frequency control we had the pole changing method. In pole changing method, we discussed three methods: one with multiple stator winding having different number of poles, second method of consequent poles, and third was the pole amplitude modulation. We have already covered this particular method as well in the previous lecture of the topic. So now let me proceed with the other methods now. So all the methods which are exercised from stator side are actually applicable for the squirrel cage induction motor as well as wound rotor induction motor. In addition with these methods, for wound rotor induction motor, as the rotor circuit is accessible, so the speed control can well be exercised from the rotor circuit. The various methods of exercising the speed control from the rotor circuit are as follows. We have got rotor resistance control, we have got cascade connection, we have got rotor voltage injection. So starting with the rotor resistance control. We know that a variation in rotor circuit resistance varies the speed of the motor, and this can very well be proved from the speed torque characteristic of the motor. This is the speed torque characteristic of the motor drawn with various rotor circuit resistances. Consider the very first characteristic, which is drawn with this solid line in the form of the solid line. This characteristic is drawn for a resistance R2, where R2 is the rotor winding resistance itself. We cannot reduce the rotor circuit resistance, we can only increase the rotor circuit resistance by adding additional resistance in the rotor circuit. So this characteristic which I have overwritten here with this red pen is actually the characteristic without any additional rotor circuit resistance. What we can see here is the operating point. This is the operating point, and corresponding to the operating point, what you can see, the operating speed of the motor is N1. right? Now, let us increase the resistance of the rotor circuit. Resistance of the rotor circuit is increased. Let it be resistance R2 dash. So, R2 dash is rotor winding resistance R2 plus R external, let it be R external 1, certain value of the external resistance in rotor circuit. This is giving us the rotor circuit resistance to be equal to R2 dash. What you can see over here, this is the characteristic corresponding to the resistance R2 dash. What we can see is the new operating point. The new operating point is suggesting that the operating speed of the motor is now N2. How to get the operating point? To get the operating point of the motor, we need to consider the speed torque characteristic of the motor and the load motor is serving. So, here in this particular case, this is considered, let me just change the color of the ink. This is considered to be the load characteristic. The intersection of motor speed torque characteristic and the load speed torque characteristic actually gives us the operating point. So, with rotor winding resistance R2 alone in the rotor circuit, this was the operating point and the corresponding operating speed was N1. With rotor circuit with somewhat increased rotor circuit resistance to a new value of R2 dash, say for example, where R2 dash is summation of the rotor winding resistance and external resistance 1, the operating point so obtained is this one and the corresponding speed is N2. What we can see, we can very well see that N2 is less than N1. So, from here I can conclude as far as the characteristic 1 and 2 are concerned, I can say that with insertion of some rotor resistance, with insertion of some external resistance in the rotor circuit, there is a reduction in the operating speed of the motor. So, now the operating speed of the motor is N2. Now, let us increase the resistance to the value of R2 double dash, where R2 double dash is rotor winding resistance plus R external 2, let it be. So, this is going to be the characteristic of the speed torque characteristic of the motor. The corresponding operating point can very well be seen as the intersection point of the motor torque characteristic and the load torque characteristic, and the operating speed so obtained is N3, where I can very well see that N3 is less than N2. So, with an increment in the rotor circuit resistance, we are getting a reduction in the operating speed of the motor. If we further increase the rotor circuit resistance, we will find a corresponding reduction in the operating speed of the motor, and the new operating point and the corresponding operating speed as shown in this figure are this, and the speed operating speed is N4, where N4 is less than N3, right. So, what we can say with an insertion, with an increment in the rotor circuit resistance, we can have a reduction in the operating speed of the motor, and this is also true that with this method we cannot increase the speed of the motor, we can only reduce the operating speed of the motor. Besides this, we can also say that from the torque speed characteristic itself, we know that torque T is proportional to Kt R2 upon S for smaller values of slip. We can very well modify the torque equation. For the smaller values of the slip, I can write the torque Te to be proportional to be equal to, as I have already taken a proportionality sign over here, I can very well write the electromagnetic torque developed by the motor can be written as Kts upon R2, or the operating slip can be written as Te, that is electromagnetic torque developed by the motor, R2, which is the rotor winding resistance, rotor circuit resistance rather, I must say in this particular case, divided by some constant Kt. So, this is actually showing that for a constant torque, slip is proportional to rotor resistance R2. So, by varying the rotor resistance R2, the slip and hence the speed of the motor can be varied. We know that if slip is increasing, it means there is a reduction in the operating speed of the motor. Slip is proportional to rotor circuit resistance. So, if we are increasing the rotor circuit resistance, we will find a corresponding increment in the operating slip of the motor, and hence a corresponding reduction in the operating speed of the motor. Now let us move to the next method of speed control from rotor side. It is cascade connection or tandem connection. Here let us consider that P1, P2 are the number of poles and S1, S2 be the operating slip for the main and auxiliary induction motor. Before going into the details, let us just try to understand what the system is. In cascade connection, two motors are connected in cascade. The first motor is the main motor for which speed control is required. The second motor is the auxiliary motor, and auxiliary motor is actually responsible for controlling the speed of the main motor in this particular method. In cascade connection, the power is extracted from the main motor and it is given to the auxiliary motor. This is cascade connection. Besides this, the two motors are coupled mechanically. This motor is a wound rotor induction motor, and in this particular scheme, the second motor as well is the wound rotor induction motor, wound rotor or slip ring induction motor. These are the slip rings of the first motor, these are the slip rings of the second motor, which is the auxiliary motor. An external rotor circuit resistance is connected in the rotor of auxiliary motor, and the output of first motor, output in the sense the power is extracted, the rotor terminals are brought to the slip rings. To the same slip rings, the stator terminals of the auxiliary motor are connected. This type of connection is said to be the cascade connection. Now, let us consider the speed control. Let us see what are the various possible speeds of operation of the main motor when we are discussing the cascade connection of the motor. So, let P1 and P2 be the number of poles for the main motor and auxiliary motor. So, P1 is the number of poles for the main motor, P2 is the number of poles for the auxiliary motor. Let the operating slip of these two motors are S1 and S2. Then for main motor, the synchronous speed would be given by 120 F1 upon P1, where F1 is the frequency of supply. Frequency of supply given to main motor. Right? The actual speed of the main motor, that is motor 1, would be NS1 into 1 minus S1. So, it can be written as 120 F1 upon P1 1 minus S1. Now, let us talk about the auxiliary motor. What supply the auxiliary motor is getting? Auxiliary motor is getting rotor supply of the main motor. What about the operating frequency of the supply given to the auxiliary motor? It is the rotor frequency of the first motor. The operating slip of first motor is S1. The frequency of supply to the first motor is F1. So, the operating frequency, so the frequency of supply given to the auxiliary motor is nothing but S1 F1. Knowing F2 equals to S1 F1, I can very well write down the actual rotor speed for the second motor or the auxiliary motor as 120 S1 F1 upon P2 into 1 minus S2. Now, neglecting the small value of slip S2 and taking and as the motors are coupled directly. Motors can also be coupled through some gear arrangement. Motors here are coupled directly. So, I can say that NR1 have to be equal to NR2. As the two motors are coupled together, the operating speed of two motors have to remain same. So, I can very well say that the ratio NR1 to NR2 must be equal to unity. We know the equation of NR1, so I have put the equation of NR1 as 120 F1 upon P1 into 1 minus S1 and NR2 as 120 F1 S1 upon P2. Why so? Because let us see, it was 120 S1 F1 upon P2 into 1 minus S2 and I have neglected, for simplification in the calculation, I have neglected the small operating slip S2. So, what I can write over here is 120 F1 S1 upon P2. It comes out to be equal to 1 minus S1 P2 upon S1 plus, S1 P1. Now, simplifying this equation, as I know, 1 minus S1 P2 upon S1 P1 is equal to unity. Solving this equation to get the operating slip S1, I can very well write S1 to be equal to P2 upon P1 plus P2, right? The actual speed of main motor and hence the cascaded arrangement is NR equals to 120 F1 upon P1 into 1 minus S1. Substituting the equation of S1 over here and solving the same. So, 1 minus S1 is given by P2 upon P1 plus P2. So, it comes out to be 1 minus P2 upon P1 plus P2. Simplifying this equation, we get 120 F1 upon P1 plus P2. So, what is 120 F1 upon P1 plus P2? It is the operating speed of main motor. Right? So, this is the operating speed of the main motor. Now, in other words, the speed of cascade set is same as that of a single motor with P1 plus P2 poles. The torques of two motors are in the same direction and hence this scheme is said to be the cumulatively cascaded scheme. Now, let us consider that the phase sequence of voltage applied to the second motor is reversed. If we reverse the phase sequence of the supply given to the auxiliary motor is reversed, let us see what happens then. What would be the new possible speed, operating speed of the setup? So, if the phase sequence of the voltage applied to second motor is changed simply by interchanging any two leads, then auxiliary motor will develop a torque in a direction opposite to the torque developed by the main motor. This scheme is then called a differentially cascaded arrangement or a differentially cascade arrangement of speed control of the motor. Now, let us see what happens under these conditions. The main motor operating speed will remain same as NR1 equals to 120 F1 upon P1 1 minus S1, right? In this particular case, the operating speed, if only the second auxiliary motor is operating, then the operating speed of auxiliary motor would be 120 F1 S1 upon P2 1 minus S3, where S3 is assumed to be the operating slip of auxiliary motor under this differential connection. Now, a negative sign is put over here just to indicate that the speed of auxiliary motor would be opposite to the speed of the main motor, which can be simplified as 120 F1 upon P1 into 1 minus S1. 120, which must be equal to 120 F1 upon P1 into 1 minus S1, which is nothing but NR1, as the two machines are connected in cascade. So, NR1 equals to NR3. We know that. Now, let us consider that if the small operating slip S3 is neglected again, then what happens? In previous case as well, we neglected the small operating slip of the auxiliary motor. In this analysis with differential connection, again for the simplification of analysis, we are neglecting the small operating slip S3 of the auxiliary motor and simplifying in the similar manner, proceeding in the manner we proceeded in previous analysis, we can say that S1 is now equal to P2 upon P2 minus P1. So, what is this? S1 equals to P2 upon P2 minus P1. Knowing S1, I can very well write down the equation of the operating speed of this cascade arrangement as 120 F1 upon P1 into 1 minus S1. Let us substitute this particular equation of S1 with differential connection in this equation of the operating speed of the setup. I can very well write it as 120 F1 upon P1, in bracket it is 1 minus P2 upon P2 minus P1, which gives us the operating speed as 120 F1 upon P1 minus P2. And this is a fact which can very well be seen from here, that this speed is possible, this operation is possible only if number of poles of the two machines are different. If the number of poles of the two machines are same, this kind of operation is not possible. Now, let the electrical power taken from the supply by the main motor stator be P. Then actually, I would like to close the speed control method over here, as it served our purpose of the speed control. This is beyond the scope of the topic, so I am dropping this particular portion from here. The next method of speed control is rotor EMF injection. Let us see what is rotor EMF injection. We know that the air gap power PG can be written as summation of SPG plus 1 minus SPG. Air gap power PG is the total power transferred from the stator to the rotor of the machine. The air gap power PG can be written as the summation of SPG into 1 minus SPG. Here, 1 minus SPG is actually representing the mechanical power developed in the motor. And what about SPG? SPG is actually the slip power, and this slip power appears as rotor ohmic loss if the rotor is short circuited, right? So, the total power input to the rotor of three-phase induction motor can be divided into two portions. One portion is the mechanical power developed given by 1 minus S into PG, and the other portion is the slip power. As it is suggested over here, the slip power will actually appear as the rotor ohmic loss if the rotor is short circuited. However, instead of wasting the slip frequency power SPG into the rotor circuit, it can very well be converted by various schemes to the useful power, which is either returned to the supply or it can also be added to the main motor shaft with some configuration, following some special configuration. The most useful method of recovering the slip power SPG and controlling the speed thereby involves the injection of an EMF in the rotor circuit from some suitable external source. So, it should be understood that the injected EMF must be at slip frequency at all the possible rotor speeds. Now, we must note that when the EMF is injected in the rotor circuit, the wound rotor induction motor actually becomes a doubly excited induction motor, right? So, when we apply the slip power recovery scheme to the motor, three-phase induction motor, three-phase wound rotor induction motor, actually under these conditions, we are operating the three-phase wound rotor induction motor as a doubly excited induction machine. Now, this is the principle of operation. Now, let us consider it is the simplified version just to explain the principle of slip power, just to explain the speed control by slip powers by injecting the slip voltage into the rotor circuit. So, for this, let us consider the rotor circuit without any EMF injection. So, this particular circuit diagram is representing a rotor with a voltage of 10 volt, some impedance of the circuit is 5 ohm. So it will cause circulation of a current of 2 ampere. The current in the circuit is nothing but SE2 upon Z2. Now let us consider the second case. In the second case, some EMF with this polarity. In this particular case, an EMF of 5 volt is assumed over here. An EMF of 5 volt is added, is injected into the rotor circuit. So what happens to the current? SE2 minus EJ upon Z2 is going to be the current now. So what I can write over here is, here what was the current? SE2 was equal to 10 volt and the impedance was equal to 5 ohm. So the current came out to be equal to twice ampere. In this particular case, the injected EMF is also there. So 10 minus 5 upon 5 will give us a current of 5 divided 5 equals to 1 ampere. What happens now? Because of a reduction in the current, because of a reduction in the current, the torque developed by the motor reduces. This causes slowing down of the motor. When motor slows down, what happens? We know that operating slip S equals to Ns minus Nr upon Ns, right? It is Ns minus Nr upon Ns. So, when rotor speed is reducing, it will cause a corresponding increment in the slip. An increment in the slip will increase this part of the EMF. It means, let us consider that the EMF SE2, because of an increment in the slip, the EMF SE2, say for example, becomes equal to 15 volts. So what about the current now? The current will now be equal to 15 minus 5 divided by 5, which comes out to be equal to 10 divided by 5, which comes out to be equal to twice ampere. So the motor current is increased to the original value of twice ampere. The motor is now developing the same amount of torque which the motor was developing at this particular instant of time, but now it is operating at a reduced speed. So that the speed control of the motor. Thank you.